have with us today Yannis Orlandos, and he's going to talk to you about embedded Swift, Linux, and he's going to tell you a lot more that I don't know anything about. So please give him a round of applause.
Thank you. So my talk is going to be about IoT and robotics with Swift, to be specific, and something that we call an edge device. So there are very many types of edge devices all around. Typical edge devices might be your phone is an edge device, satellites are types of edge devices, hopefully soon humanoid robotics, your Roomba. There are so many types of edge devices, and all of them share one thing in common. They have a physical manifestation, usually nearby you, not in a data center. They're related to hardware, sensors, and they do some local processing. So they're not just a dumb sensor. And if any of you has ever worked with these types of devices before, you know that not all of them are equal. Because some of these are really, really hard to develop for. I've never done satellite development, but anything robotic arm or embedded Linux, maybe on the Roomba, all of that can be pretty painful to set up compared to some other technologies. So I've tried to basically demonstrate how easy it is to get started with certain technologies. Like getting started with a website is very easy. You just open an HTML file, you type some basic HTML. You can get up and running within a couple of minutes, if that. An iOS or Android app is also pretty easy. You might need to install like an IDE, some basic developer tools, but they're just a one script setup or like a one-click install, and then you create a new project and you're ready to go. You can just install it on your phone. Embedded Linux gets a bit harder. Now we have to think about what OS am I running, what technologies am I using, what programming language, what libraries, and then even before you get to anywhere near production, the amount of choices that you have to make are like exploding, right? So it becomes very difficult. And microcontrollers are also very difficult. They have a lot of the same choices, but they add a lot of the hardware choices on top. And there is no debugger support or like hand-holding as you're used to in other platforms, right? Like if your HTML page is not rendering correctly, your web browser will scream at you and say, well, this is, you're not closing this tag maybe. On iOS development and Android, your compiler will start complaining. With microcontrollers, your compiler will complain if you do very gross mistakes. But if it's anywhere nuanced, like, hey, you've got a race condition, or I don't know, like you're leaking memory, there's no way they will help you. So this adds a lot of friction. And anytime you add friction, prototyping becomes slower because your incremental cycles, every cycle that you spend for, build, debug, release, getting feedback of what your application is doing becomes painstakingly slow. So what we see a lot of developers do is they write their code in Python. And Python is a great language, right? It's very easy to write, and at the same time, it runs in MicroPython, so it runs on all types of devices. But it's not very fast. If you need anything performant, it's not going to be your solution down the line. So what a lot of developers do instead is they use C++ for the performance. But then your iteration cycles become very slow. So what a lot of people in the industry, unfortunately, have been doing is they write their code in Python, prototype, and when it's ready for a release, they rewrite everything in C++, which is going to be great, right? But obviously, the developers who wrote this are very confident with C++. And vice versa. So your C++ developer knows exactly what to do in Python and how to read it. So this becomes a little bit hard. And besides that, if you want to find any type of documentation on embedded Linux or microcontrollers, tutorials and content are hard because there are so many choices and ecosystems that you can work with, right? And each of them have their own articles, their own documentation, their own library ecosystem, their own package manager, their own build system. And if you started with C++ and find the Rust tutorial, you're out of luck. So what do? How are we going to break this cycle? First of all, a bit about myself. I'm Yannis. I have been doing backend development ever since I was 12. And about 10 years ago, there was this new language that I found through a friend of mine called Swift. And the first thing you do when you have a new language and a new ecosystem, and there are no libraries, is you start building web frameworks because that's easy, right? No, it's not. But you learn a lot this way. So the first things I did before I started building my first website was building the Vapor Web Framework and building a couple database drivers so that I could get started. Very naive, but through a painstakingly slow and year-long process, it did work out, and people are using Swift on backend, on Linux. These days, I'm part of the Swift open source project. I'm part of the Swift server working group together with various teams like Apple and AWS, Amazon Prime Video, all sorts of teams that use Swift on the server to empower their backend services. I'm also part of the Android workgroup, which was recently created, where Swift, Apple's programming language, is coming to Android for cross-platform app development. And I'm working on various other bits and bobs around the ecosystem. I have a blog about server as well. So why did I choose Swift? Well, Swift has a couple nice properties that I think are very interesting, not only for mobile development, but also for server, for Linux, and even for embedded. And it starts with these three main principles that Swift really likes, which is being fast, being expressive, but definitely being safe. So when we're talking about fast, I don't necessarily just mean being fast like Python. It's not just fast to develop. We're really talking about performance. So whatever code you write needs to run at C or C++ speeds, or very close to it. But when you have performance, usually this comes at a cost of maintainability or readability. So you need abstractions that are very efficient too. Things like classes, object-oriented programming, but also something new that we call protocols, which is basically an abstraction that you can apply to your types. We have concurrency that scales. We have a real good concurrency ecosystem with async await from other languages, but we've made it part of the language's syntax in a structured way so that whatever code you write is, you can read it from top to bottom, basically. Like for loops for consuming streams, stuff like that. And a very big one is that whatever performance footprint your application has is very predictable. For example, we don't have garbage collection, so your application will not freeze the world every so often, but we have automatic reference counting just like Rust. So once you don't use a type anymore, the counter at 0, you don't use the type anymore, it gets deallocated at that moment, instantly. So it's also expressive. So we have a concise, readable syntax, maybe a bit weird for people coming from other languages, but it's very C-like. We allow many different paradigms, like functional programming. We have a very, very strong generics ecosystem in our language, which plays into the previous abstraction layers a lot, kind of a synonymous to C++ templates. And finally, we're safe. Not only is Swift a memory-safe language, but it's also data race-safe. Compile time, before you even run your first application, Swift will complain about all sorts of things that you might have done wrong, like two threads are accessing the same shared mutable state. And while at first it might be a really annoying thing that Swift seems to complain every 2 seconds, these are real problems that you are not deploying in production, that you've never even been able to run in production. Before this first application runs, you know that all sorts of checks are working. And some things that cannot be checked, like accessing an array or like a pointer. There are bounce checks on basically every type. So if you try to access an array's element, Swift will check that the bounds are safe and it will crash the application at runtime before it will allow you to get into all sorts of vulnerabilities that you're used to in other languages like C and C++ that don't do any hand-holding. But this comes at the cost of a lot of footprint, I assume. Well, it can add footprint if you use a lot of standard library features or like other dependencies. But a basic Swift application, especially with embedded Swift, can be kilobytes in size. Even 100 bytes if you go really, really small and just do a hello world. And also the memory footprint is tiny. One of my main problems when I deploy Linux services is not the fact that I can't get a big enough node. The problem is that I can't get a small enough node. A lot of the time, AWS only offers me the smallest tier of 128 megabytes of RAM. And I don't need even half of that, which is great for embedded and not so much for my wallet. And finally, Swift has a really cool ecosystem in interoperability. So even if you're using another language right now today, and you have packages or code that you want to port to your that you want to bring with you when you use Swift, All of these languages have interoperability libraries, either in the language with C and C++, or with C#, Java, Node.js, and Python. There are packages actually out there today that allow you to bidirectionally bridge C and Swift code to that language and from that language. So you can invoke Java functions from Swift, not on embedded Linux, not on embedded devices like microcontrollers, because Java doesn't run there. At least I hope not. But you can bridge the functions bidirectionally. So if you have a Swift function and you want to expose to Java or a class, you can. But the other way around works as well. So Swift is today used in a lot of ecosystems. We call microcontrollers. For example, Apple Secure Enclave, which is the processor that keeps your private keys private. On Android, there are companies using Swift already, Readle and Cricket, which have Android apps written in Swift for both iOS and Android in the same code base. There are 3 desktop browsers, Dia, Arc, and Ladybird, that are integrating Swift in their code base. Dia and Arc are both by the browser company and are almost entirely written in Swift. Ladybird started their C++ migration to Swift for new components. Finally, for cloud, Apple uses it, but also Amazon Prime Video has written their backends in Swift. And for web, there has been GoodNotes. GoodNotes is a iOS app that bridged a lot of their business logic to be cross-platform using WebAssembly. So Swift is a proven language across many ecosystems, including microcontrollers, including Linux, so you can use it today. So how does that fit into accelerating IoT and robotics? Well, how does Swift help? I've got a new project called EdgeOS, which helps you bridge your Swift code bases or other code bases to your Linux or microcontroller platforms. We like to embrace a lot of the same principles that Swift admires to. For example, we're fast. That means that we not only can iterate our code in Swift, but we can deploy it in Swift as well. So we don't need to rewrite our code base in a new language every time we want to deploy. We're expressive, so it's easy to iterate your code. Not only can you write your code and read it too, the iteration cycle is much easier because even junior developers can understand the more ergonomic syntax. And the memory and data rate safety will hopefully lead to a lot less vulnerable devices in the network of IoT devices. And the interoperability allows you to bridge your existing code bases over to Swift and integrate Swift wherever it deems is necessary, right? So if you have a new networking component as part of your C++ microcontroller, you can do that new code, the networking I/O, in Swift, and leave the rest as C++ as is. No need to rewrite everything today. So what is Edge? Edge is a set of components and libraries that we provide. There's an OS that we provide that's all open source with a set of core frameworks based on the open source community and some of our own. We have some advanced frameworks that we are working on as well, which I'll get to in a bit later. We have an IDE extension for Visual Studio Code, command line utilities, so we can integrate it with other IDEs, and we have a couple other fancy things planned for the future that I won't get into today. So what does this enable? Write code once, run anywhere, even on microcontrollers. That's our dream. We want to make sure that whatever code you write, if it's an HTTP client or whatever, you have your business logic once, and whether it's Android, iOS, whether it's a microcontroller or Linux, that code, that business logic runs for you. And it runs the same. So I want to give you a bit of a demo of how EdgeOS is used before I dive into the specifics. Because there are only really 3 steps that we strive to provide. The first one is you need to flash EdgeOS. So hopefully this works. There's an IDE extension in Visual Studio Code or Cursor, and you simply plug your SD card or NVMe disk somewhere in, and there is a disk that should appear over here. So you click on the disk, you flash it, select the device that you're trying to flash for example, a Raspberry Pi 5, or a Raspberry Pi 0, or maybe an NVIDIA Jetson when you need GPUs, and it starts flashing. And then once it's done, after, depending on whether or not you still need to download the image, it can be a couple seconds, it can be a couple minutes, the device, the SD card is ready, you can just get it out and plug it into the device. I don't think I'll wait for the last few seconds, but that's the gist of it. Then as soon as your device is as soon as your SD card is plugged into the device, there's only a simple step of plugging a USB cable into that new device, so it boots up. And this gives it power, but it also gives it data. So your tools will start recognizing that there is a EdgeOS device, and it should show up over here in a couple seconds once the Linux has booted. And that's all you really need to get an EdgeOS device ready to boot. All of this is open source, and you can reproduce this even for other ecosystems. So we've got a EdgeOS device that has the OS. Your MacBook, Linux machine, or Windows machine, whatever development machine you use, recognizes this device as being attached to the computer. And if you create a simple Hello World Swift application, that's it. You hit run, the debugger works, the breakpoints work, and you can start working on your embedded Swift code, or even Linux Swift code. So EdgeOS itself is an immutable OS that with one USB cable can do the data and the power. Wi-Fi can be set up as well. You can share your Wi-Fi from your laptop to your EdgeOS device, so it has local networking. It's got a gRPC server embedded in it with an open spec, so that you can write your own tools for running your own apps or interacting with the CLI, with the server. Maybe you need to do some custom stuff, like extracting logs in a way that we don't yet support. And we have entitlements. So if you have multiple EdgeOS apps running on the same device, they could maybe, we're working on making sure that they both can access the camera, or in the case of GPIO, only one of them can claim a pin to interact with that pin. So you hit run on the project. Over here, you select your device. In the Visual Studio Code, you can hit the Run tab. You hit Run. You can place breakpoints. And as soon as the application launches, your breakpoint hits. The debugger works, LLDB. And this doesn't necessarily only need to be Swift, but we focused on Swift. The last step is just observing your results. So there are a lot of steps that we try to skip, that we try to automate for you, but you can do all of this yourself if you want to. You're not locked in, but we try to make it as easy as possible to get to these 3 steps as quickly as possible without you having to spend hours upon hours of figuring out, how do I install an OS? What OS do I pick? Well, I've got a Raspberry Pi, but it's got no network, and now I need to attach a monitor and keyboard because, well, it doesn't have a network. And then I need to install SSH, then I need to connect to Wi-Fi, and now I can do everything remote. Like, those kinds of pains are going to be resolved this way. Because when friction increases, prototyping becomes slow. So we're trying to reduce the friction as much as possible. And this is our aspiration. I think we're pretty close already today to this. EdgeOS has been incredibly easy to set up for many people. We've got people that are using it for the first time and have their first app up and running in 15 minutes or so. Hello world, but hello world. So how does it work? So EdgeOS is a small Yocto-based image. It's layered, so Yocto is a layered ecosystem. So I'm not the expert on Yocto, to be honest, but you have hardware layers that you can insert into your Yocto build, so that your OS is built for either Raspberry Pi hardware or NVIDIA Jetson Nano, with GPU support, and these drivers, they reside in a layer. So we can swap that hardware layer depending on the image we're producing. And then on top of that, we have a couple basic necessities. We have Containerd, a network manager. Containerd allows you to run containers, and we didn't opt for Docker because we wanted more control. Right now, today, if you use any containers on a Linux machine, most likely you're using either Docker or something similar. And Docker you need Docker to be installed on your development machine to build the image, and then you need to upload that image to your device, which can be long depending on the dependencies you have, how many dependencies you have, and then once that's uploaded, you can only start running it. We're trying to make sure that we optimize the layers as much as possible by creating a custom container management. So we directly talk to Containerd over gRPC as well, so that we can manage the layers for Containerd, so that we can optimize how much time is being spent on uploading the dependencies that you've already used in a different run cycle. We optimize the upload speeds. For example, if your binary is mostly the same, The binary might be 50 megabytes, for example, but if only 4 kilobytes change, we can upload a diff there. So you're only really uploading the 4 kilobyte diff. And we're really making sure that every kind of friction in the iteration cycle is reduced. So Edge Agent is the gRPC server where you can upload your containers with our CLI. And that orchestrates to Network Manager whether to connect to a Wi-Fi network or connect with a Bluetooth device. It orchestrates to containerd what needs to happen as well, what permissions your app has, for example. Can your app even access this hardware device like GPIO? And then your app on top is just an OCI container image that we either package for you with our runtime optimizations in terms of reducing the upload time. But you can also just upload a raw container and handle it yourself. We support that. And then on your dev machine, we have a Swift toolchain that we manage for you, or you can use the standard toolchain, that's fine as well. And then we will install it for you just to get it started quickly. We have some basic CLI tools that have a gRPC client, and a gRPC client then connects to the EdgeOS device and discovers it and does that kind of stuff. So what's ready today? Well, Swift already runs on microcontrollers and has got a growing ecosystem on Linux. Like 40% of the Swift packages today run on Linux already, with 30% of all packages also running on Android, which is a new emerging ecosystem. So this really shows that the ecosystem and the community is very happy for other ecosystems to be part of this community. It's not just iOS. The remainder 60% are largely iOS UI-focused libraries, which obviously don't work on Linux, which has an entirely different UI ecosystem. We also have UI libraries for Linux, like GTK implementations, one of which was actually even made by an intern at GNOME. And Miguel de Casa, the founder of GNOME, is currently working on game development with Swift on Linux and Windows. So this is definitely going the right direction, and Apple is pushing for it too. We have a VS Code extension for Swift as well. And you can use Swift anywhere you have an LSP, although the Edge tools are only available for Visual Studio Code today. The CLI can still be used as well. We support remote debugging out of the box. It will be all set up for you. And then the one-click run and debug cycle also already works. We also have basic hardware support, but the abstractions are not super high level. So you need to specifically find a dependency for GPIO on Raspberry Pi or on your NVIDIA Jetson. If there's any incompatibilities there, you need to take care of that yourself today. We're hoping to get like a hardware abstraction layer in place so that we can manage a bit more for that for you in there, so that you don't, at least as little as possible, have to manage how do I migrate from an NVIDIA Jetson to a different type of hardware platform. Next up, we'll also have a couple other projects that we're currently working on, all in the open. We're working on Edge AI for machine learning inference, which is also going to be available anywhere Swift runs, so Windows, Linux. It doesn't need to be EdgeOS. We're working on a high-level networking library called TAPS. And TAPS is intended to be handling things like the disruption-tolerant networking, also basics like TCP, UDP, TLS, DTLS, but also more fancy things like mesh networking are things that we're very eager to integrate into a framework called TAPS. TAPS is intended to run on both microcontrollers, Linux, and all platforms alike. So our aspiration is to get in the coming months a basic version of TAPS that runs on all of these platforms with all of the features I just mentioned. We're also working with some people to implement physics and inverse kinematics so that you can control your robot arm. For those unaware, inverse kinematics, it's pretty easy in physics to compute how to do certain basic movements. It's very hard for me to explain inverse kinematics as well. But basically the idea is that if you have a robot arm and you want to grab a ball, that ball is over there. But you can't just snap over there because there are multiple joints in my arm that you need to move. So what inverse kinematics does is it tries to reach as far as possible with my upper joint, which is not going to reach, and then it will pull on the other joint to make the rest of the movement work. So we're working on inverse kinematics libraries in Swift and C++ as well, and we're trying to integrate all of your existing C++ libraries that you have already available today in Cmake and bring them over to Swift. Another thing that we're very eager for is to help with fleet management. This might be partially open source and partially closed source. We're not sure how it will exactly work, but we want to make sure that it's easy to roll out your devices, and also roll out updates, get observability going, all of the things that you need in a production setting environment. And finally, Swift has a really good concurrency runtime, but it's not available on embedded today. It doesn't work yet on microcontrollers, but I think it's very, very essential for a tool like concurrency, which is all focused on I/O, to come to microcontrollers, because that's basically all they do. So you can visit our existing work here today on GitHub, see if you want to contribute, join our Discord community or somewhere else on the forums. We have 2 websites up right now. The second one is a bit work in progress, so if you visit there, you'll see a lot of not working website components. The edgeOS.io definitely already works. And thank you. If you have any questions, let me know. And otherwise, I'd like to speak to you after the conversation.
Are there any questions? Does this one?
Hi there. Thanks for the talk. You mentioned a hardware abstraction layer
Correct.
that you're still thinking of or working on.
Yes.
If I'm correct, edgeOS is built on top of Yocto. So wouldn't
It's written
so
on
it's
what?
built on top of Yocto.
Yocto, yes, correct.
So wouldn't the hardware abstraction be covered by Yocto already?
I think so in part, but I'm also thinking about, so if you have a USB device and you want to attach it to a OCI container, that device now effectively owns the device, right, the hardware device. But in some scenarios, like a USB camera, it's just reading data. You're not writing back, right? Or like a microphone. There might be multiple apps listening to the same microphone. And we don't want you to exclude, wall you into a scenario where you can only read the microphone from one app at a time. So we want to kind of multiplex that in a way, or split up the stream so that multiple devices have multiple containers have an easy way of reading the same data. So that you can, do that in multiple apps at the same time.
Okay. Love the clarity of your talk and your answers. Are there any more questions? Over there. I'm going to be running.
At work, we're currently debating whether we're going to put a Raspberry Pi or an Orange Pi in the device for fleet management. That's on your to-do list.
Yes.
What's the hardware looking at for the foreseeable future?
The hardware?
Well, you've got single board computers.
Yes.
Raspberry Pi is just one of many.
Yes.
There are lots of knockoffs. How easy would it be to get the other ones working with this setup?
I don't know if we've tried the Orange Pi yet, but we've tried a large set of devices, and the Raspberry Pi image just works on a lot of them. But we don't, until we test it, we can't really guarantee that, of course. We're kind of in a bit of a debate whether or not we want to support more hardware devices and expand that way, or we want to reduce the amount of hardware devices we officially support at first, just so that we can make more progress on other aspects. But you can make an edgeOS image with your own hardware layer on Yocto yourself, and that's not too hard, luckily, so we offer support there as well.
I think it's the exact same hardware, same chips, same.
Yeah, I think
everything.
so too, right? So no, then it will just work. But until we test it, I'm not sure.
Okay, thank you.
Yeah.
Thank you very much. Well, if there's no more questions. Oh, wait, we have a question back here. You're going to have to come this way because of the sound.
You were calling your embedded OS edgeOS, right?
Correct. Yes.
As I recall, EdgeRouter calls its firmware edgeOS as well. How do you plan on handling that duplicate?
That's been an unfortunate thing that's been on my mind as well, because we figured that out way too late. Right now we're calling it edgeOS. I'm not sure if we can keep it that way. But that's a good remark.
Good point. Do we have any more questions? You've been very clear. Thank you so much. Well, give him a round of applause.
Thank you.